Hello friends, in previous lecture we have studied concept of ratio test for absolute convergence. In this lecture we will study root test and one example from ratio test. Okay. Discuss the convergence of series summation of x raised to n upon n equal to 1 to infinity. So solution so here for series summation of n equal to 1 to infinity x raised to n upon n given series is summation of n. Case 1 for x equal to 0 summation of x raised to n upon n is 0. Case 2 if x not equal to 0 then mod of m plus 1 upon n equal to mod of x raised to n plus 1 upon n plus 1 into n upon x raised to n, and this will become x raised to n into x into n upon n into 1 plus 1 upon n into x raised to n. This x raised to n get cancelled, n get cancelled, and it will become mod x upon 1. Okay. Therefore, limit of this mod of m plus 1 upon n is equal to limit n tends to infinity of mod x upon 1 plus 1 upon n is mod x upon 1 plus 0 is equal to mod x. So, by ratio test, summation of n is equal to summation of x raised to n upon n converges absolutely if mod x less than 1 and diverges if x greater than mod x greater than 1. Okay. Now for x equal to 1, summation of x raised to n upon n is equal to summation of 1 by n is divergent, and for x equal to minus 1, summation of x raised to n upon n is equal to summation of minus 1 raised to n upon n is convergent. Case 3. Okay. Convergent by fundamental result on alternating series. Because 1 upon n goes on decreasing and limit of 1 by n is 0. Therefore, that alternating series is convergent. So, from case 1, 2, 3, case 1, 2 and 3, summation of x raised to n upon n is convergent. It's convergent absolutely for mod x less than 1 and convergent for x equal to 1 minus 1 and diverges otherwise. So, I have completely discussed the convergence of summation of x raised to n upon n. For x equal to 0, I cannot use the ratio because x raised to n occurs in denominator and I cannot divide any time by 0, and that's why I have taken x equal to 0 case separately. x equal to 0 case separately. Is it clear? So now we will study root test. If lim sup of nth root of mod n, if lim sup of nth root of mod n equal n tends to infinity is equal to a, then 1, a less than 1 implies a summation of n converges absolutely. Second, a greater than 1 implies summation of n diverges. And third, a equal to 1, then test fail. A equal to 1, then test fail. Okay. So proof of this is too simple. Again, first, if lim sup of nth root of mod n is equal to a less than 1, then choose B belongs to R such that a is less than b less than 1. Then b is equal to a plus epsilon for some epsilon greater than 0. Now since lim sup of nth root of mod n is equal to a implies this, for epsilon greater than 0, nth root of n mod n is less than a plus epsilon is equal to b except for finitely many n's. Many n's implies there exist positive integer n such that nth root of mod n is less than b for every n greater equal n, and therefore mod n is less equal b raised to n for every n greater equal n. This implies summation of n is dominated by summation of b raised to n 1. Now summation of b raised to n equal to 0 to infinity is a geometric series with ratio b belongs to 0 1 and hence convergent and converges to 1 upon 1 minus b. So from 1 to and comparison test, 1 to and comparison test, summation of n converges absolutely. Now let's see second point. Case 2, if a is greater than 1, if a greater than 1, then again I can select B such that, then choose B belongs to 1A, therefore B is equal to A minus epsilon for some epsilon greater than 0, for some epsilon greater than 0. Since lim sup of nth root of mod n is equal to A, therefore for epsilon greater than 0, nth root of mod n is greater than A minus epsilon is equal to B for infinitely many n's, and this B is greater than 1 for infinitely many n's. As n's, which implies is mod n's are greater than b raised to n greater than 1 for infinitely many n, implies is limit of n tends to infinity must not be 0, Therefore, by sufficient condition, necessary condition for convergent series, summation of n is divergent series. Okay. Case 3, if A is equal to 1, then to show test A. So for divergent series, summation of 1 upon n equal to 1 to infinity, limit n tends to infinity of nth root of 1 by n is equal to limit of 1 upon n raised to 1 by n, and we know that n raised to 1 by n approaches towards 1. So this is 1 upon 1 is 1. Similarly, for convergent series, summation of 1 upon n square, limit n tends to infinity of nth root of 1 upon n square is equal to limit of n tends to infinity of 1 upon n square raised to 1 by n is equal to limit n tends to infinity of 1 upon n raised to 1 by n its square, which is 1 square, is equal to 1. So from this, test is not applicable. Root test is not applicable if A is equal to 1, right? Now I'll take the examples from exercise 3.6. Exercise 3.6. In that first, true or false. True or false. If summation of n is convergent series of non-negative numbers, if summation of n is convergent series of non-negative numbers, and summation bn is a divergent series of non-negative numbers, then summation of an is dominated by summation bn. So you have to check whether this statement is true or false. So given statement is false. Justification. We'll consider series. We know summation of 1 upon 2 raised to n equal to 0 to infinity is convergent series of non-negative numbers. Right. Now, I have to check whether file 1 plus half plus 1 plus 1 upon 2 square plus 1 plus 1 upon 2 cube plus the dot etc. is divergent series of non-negative number is equal to, this is your summation n, this is summation bn, is divergent series of non-negative numbers such that summation an is not dominated by summation bn. You can observe. Summation n is not dominated by summation bn because after sum n all n's must not less equal bn's. Is it clear? These terms, there is no any relation. Or here if I take, say, I want to this is summation of 2 raised to n, so I will get second term to be 1 half there. This is 1 upon 2 cube, this is 1 upon 2 raised to 4 there, and here I am getting 1 upon 2 square. That 1 upon 2 square is not smaller than that, okay? So this is correct one. This is correct, no problem. Because in summation of n, that terms are greater than that. That terms are greater than that. Discuss the convergence of following series. Question 2. Convergence of following. In that A, summation of n raised to 4 upon n factorial. If I denote this by summation n, Here an plus 1 upon an, as terms are positive, so I am not giving modulus sign. So n plus 1 raised to 4 upon n plus 1 factorial into n factorial upon n raised to 4. So by taking n raised to 4 outside, okay, or firstly n plus 1 into n plus 1 cube into n factorial upon n plus 1 into n factorial into n raised to 4. So in this way I will take it. But if I take this n raised to 4 as it is, this n factorial get cancelled, and then this is nothing but n raised to 4 into 1 plus 1 upon n raised to 4 upon n plus 1 into n raised to 4. This n raised to 4 get cancelled. Okay. So therefore limit n tends to infinity of n plus 1 upon an is equal to limit n tends to infinity of 1 upon n plus 1 into limit n tends to infinity of 1 plus 1 upon n raised to 4. This will become 0 into 1 plus 0 raised to 4, which is equal to 0 less than 1. And therefore by ratio test given series is convergent. Therefore by ratio test summation of n raised to 4 upon n factorial is convergent. B. Summation of 1 plus n upon 1 plus n square. 1 plus n upon 1 plus n square, n equal to 1 to infinity. If I take this, so here if I compare this with summation n, okay, here an is equal to 1 plus n upon 1 plus n square is equal to, by taking n outside, n in bracket 1 plus 1 upon n square in bracket 1 plus 1 upon n square. This one n get cancelled. And if you observe, as n approaches towards infinity, 1 upon n goes to 0. So these are approximately equal to 1 upon n. I will take this as bn. This as bn. Now limit n tends to infinity of an upon bn is equal to limit n tends to infinity of, what is this, 1 plus 1 upon n upon n into 1 plus 1 upon n square into bn. Bn is 1 upon n. So n, this n get cancelled, and then this limit will become 1 plus 0 upon 1 plus 0, which is 1 not equal to 0. Moreover, summation bn is equal to summation of 1 upon n is divergent. Therefore, by limit form of ratio test, by limit form of comparison test, summation of n is equal to summation of 1 plus n upon 1 plus n square is divergent. This series is divergent. Summation of 3 upon 4 plus 2 raised to n. N equal to say 0 to infinity or 1 to infinity, that doesn't matter. Okay. So this is summation of n. So here n is equal to 3 upon 4 plus 2 raised to n. This is less equal 3 upon 2 raised to n for is equal to bn for every n. Is it clear? Okay. For Rn, and summation of Bn is equal to summation of 3 upon 2 raised to n equal to 0 to infinity is equal 3 into summation of n equal to 0 to infinity of 1 upon 2 raised to n, which is 3 into 1 upon 1 minus half, which is nothing but 6. Since summation of x raised to n equal to 0 to infinity is 1 upon 1 minus x for x belongs to 0, 1. Okay. That is summation of bn is equal to summation of 3 upon 2 raised to n is convolution. Okay. Therefore, by comparison test, okay, comparison test, summation n, I am not taking modulus sign because n is positive, is equal to summation of 3 upon 4 plus 2 raised to n equal to 1 to infinity or 0 to infinity is convolution. So, with this discussion, we'll stop our this lecture here. Thanks for listening lecture carefully. Bye bye.